Swayam Prabha. Digital India. Educated India.
Let us come to thermodynamics, and the topic that I'd like to discuss today is basically what is called the phase equilibrium. So, phase as you know that a substance like say water, take for example water, can exist in various phases, in three phases, but particularly three phases, particularly for water. For if you take water at 1 atmosphere, then above 100 degrees centigrade, it prefers to be a gas. Water prefers to be a gas when the temperature is raised above 100 degrees centigrade at 1 atmosphere. And it tries to be in a solid state or prefers a solid state below 0 degree centigrade. So that is the preference given by any system, and that depends on the temperature and pressure. So the state of a thermodynamic system is determined by, or a phase of a thermodynamic system can be determined by temperature and pressure. So a system means a thermodynamic system can exist in several states or phase, and each phase can be characterized by a temperature and pressure. Each phase can be characterized by temperature and pressure. Now, which phase is stable for a given temperature and pressure is an important question. So, which phase is stable for a definite temperature and pressure? So that is the question. Now, the question of stability of a phase is an important thing. As you see, that stability of a thermodynamic system or the stability of a phase or a state depends entirely on the free energy, on the free energy of that phase or state. So if as you can lower the free energy, it prefers, the system tries to be in that particular phase. So the lowest free energy, so the system tries or prefers to be in a phase which has a minimum free energy, say G. So the important point in monitoring the phase of a system should be the free energy. So let us go back to free energy and how this the change of free energy can be manipulated for different phases. Let us for that. So we know that G is a free energy that is defined by H minus Ts. Then the change dG is basically dH minus Ts, and that is dE plus P dV plus VdP minus so it is minus TdS minus SdT. So now this dE plus PdV according to first law is basically dQ reversible, and that dQ reversible is basically TdS. So TdS plus VdP minus TdS minus SdT. So TdS cancels out, and I have dG, the change of free energy, is VdP minus SdT. And so this is for n moles of the one component system of an one component system. Then what we do, we divide it by n so that I get this quantity, the free energy change per mole. That means I write it d nu equal to, and I write this V as molar volume, the volume per mole times dP minus molar entropy, that means entropy per mole times dt. So this is basically a master equation which we would like to use for this particular discussion. So this means that the chemical potential is a function of pressure and temperature, as we needed that we want to search a phase which is really stable. So for that I'm employing this chemical potential, change in chemical potential for our purpose, and see what this thing is. Now you remember that we have immediately two conclusions that we can draw out of it. This is d nu del P at constant T. It is just the molar volume, and another is del mu del T at constant P. It is basically the minus of entropy term, molar entropy. Now you see that if I look for the mu versus T curve, that is mu as a function of T depends on a slope like this, because S is always a positive quantity, V is always a positive quantity. So this is a quantity, so mu versus T gives me a curve which is basically a line with a negative slope. So that is a line with a negative slope. is larger, much larger than molar volume of the liquid in most cases, and this is for solid. So we know that these are the things that that will help us to plot the mu versus T curve. So we use the mu versus T curve. How does it look like? So say this is mu and this is T, and so it means that mu versus T, and S being a constant, and S is basically a slope for mu versus T curve. So S is a slope for mu versus T curve. That means for mu versus T line, so the slope is highest for this gas, because this is the largest entropy. Molar entropy is largest than the out of the three phases: gas, liquid, and solid. And so, if I plot this mu versus T, then I can write it. This is for solid. This is I am plotting mu versus T for solid case. And then the liquid curve, for the liquid curve, mu versus T will be slightly stiffer. So it goes like this. So it is basically for the liquid. Now for the gas, S is the largest. So the slope, the negative slope, that slope will be highest for this case. So it has the largest slope, then the solid has the least slope, and then the liquid, and this is basically for the gas. And they are basically the lines denoting the values of the chemical potentials. So now what we do, I would like to search for the minimum for the chemical potentials. Now you see that there are certain crossing points, important crossing points. This is the line for the gas, and this is a line for the gas, and this is for the liquid. So this is a crossing point, and this crossing point can be denoted by a temperature T B. It means the chemical potential at this point for the liquid state and chemical potential for the gaseous state are equal. So for at TB, the boiling point mu of liquid at a constant at TB definite pressure equal to mu of solid, mu of gas TBP. So entire thing has been done at constant pressure. So pressure constant means this is a constant parameter. So this is a condition that is applicable for this point, which equates the chemical potential for the two phases. So that's the point. Now there is another crossing point. This is a solid line, and this is a liquid. So at T. So at this point, at say I call it Tm, melting point, you have a crossing of the mu versus T curve, and that crossing is basically is called the melting point. Melting point. And here what you observe is a mu solid at Tm melting point at a definite pressure equal to mu liquid at Tm at definite pressure. So at this point, now this is so we have identified the melting temperature and the boiling temperature in this curve. Now, which phases are really stable phases? So you can see easily that this is the minimum when you below Tm, that is below the melting point. So below the melting point, this you see the solid line is the stablest one. So below Tm, mu is minimum for solid phase, and above Tm, you see this is basically this is the minimum. So above Tm, above the melting point, chemical potential is minimum for the liquid phase. So this is for the solid, this is for the liquid phase. Now again, this is a point where you see again that, so here Tb below your boiling temperature, you have these states. This is the minimum. So below your Tb, chemical put mu is minimum for liquid phase, and here is the minimum line. So above Tb, chemical potential is minimum for gas phase. So we could figure out the different states of the system. So at this point, the solid and liquid coexist, and at this point, the liquid and the gas phase coexist. So these are the points to be noted, and we, for our search for the phase which is the stablest one. So this allows us to understand that this is the liquid phase and this is the gaseous. Always this is the minimum line. So the minimum, the chemical potential that determines that phase. So fine. So we have taken everything. Well, we have taken the everything or this picture when the temperature, the pressure is basically a constant thing. So if the pressure is constant, now if we change the pressure, what will happen? If we change the pressure, so variation, so mu versus T, variation of pressure. So how chemical potential changes with pressure. That means the chemical potential changes with pressure according to this equation. That means that is proportional to your, that is equal to your molar volume of the. So if we look at any of these carb, so what will happen, that if we take, for example, any of such carb, mu versus T carb, say this is mu versus any carb, then if we increase the pressure, this is mu versus T carb for a definite pressure, say P, then if I increase the pressure, since this is positive, the line, every point on this line will be raised uniformly. So there will be another line, if I another line parallel to it, which for which you have a higher pressure. If I lower the pressure, what will happen? The same thing in the opposite direction. So if I lower the pressure, you see that you will get, for all the points in the mu T curve will ultimately lie on the dotted line in this way. So this is a reduced curve, so it is say P minus some delta P curve. So if this is the thing, then you will note that this difference is largest for a gas. This difference will be largest for a gas and smallest for the solid. So let us look at this picture and try to find out how this gets this gets modified when I reduce the pressure. So if the pressure is reduced, we find mu versus T curves dotted line. So I draw it again for this case, that is mu versus T. Then our solid curve was this one at higher pressure. So if the pressure is low, at a reduced pressure, this line will be this one. When the pressure is reduced, we get the dotted curve, and this is for solid case, solid line. Now we look at the other curve. This is now for the liquid. Say this was the original curve, mu versus T curve for the liquid. Now at reduced pressure, the mu versus T curve appears in this way. So initially we had a point here, meeting point of the two solid lines. That was my melting point, and now the crossing has been shifted slightly to this point. Two dotted curves cross. So this is Tm prime. So the melting point is lowered. So melting point, so T reduction of pressure reduces or lowers the melting point from Tm goes to Tm prime. And now you see that the same thing will happen to the gaseous state also. This is for the gas in the initial state, and we reduce the pressure. So for the gas, the change is much larger. And initially, this was my boiling point. Tb was the boiling point, and we see that the boiling point has been shifted to a new one, that is Tb prime. Lowers the melting point, also lowers the boiling point. So Tb goes over to Tb prime, as you see from this figure. And you can see that because of the change of volume, change in molar volume is large for the gas, the Tb minus Tb prime, Tb minus Tb prime is greater than Tm minus Tm prime. That's automatically follows. So you see that we can show how mu versus T curve can actually help us to understand a very major point, that is the stability of a particular phase. As you change the pressure, if you increase the pressure, the melting point will be increasing. The melting point will be raised to higher value. If you reduce the pressure, the melting point drops to some other point, and similarly it is for the boiling point also. So these are the basic considerations that we have shown here. Now we go for two other cases, that if we look at it, that if we can reduce the pressure, we can move this mu versus T line so as we wish. So if we reduce it to a large extent, we can see something new. But before that, we also introduce another important point here, that another point that I forgot to mention, that here it is so if you stay at this point, say at x, if I stay at this point x, which is a point, and this point lies at a chemical potential which is higher, corresponding to a point which is shown in the solid curve. So if this point x, so point x is unstable point, but immediately if you find that slightest disturbance is there, it immediately drops to this point. So but note that although it is below Tm, that below the melting point, you are still in the liquid phase. So x is a point which is unstable, and it is still liquid phase. unstable liquid phase. Now, a slight disturbance may actually create a change in the system so that it immediately drops to this particular point x prime. Say if I write it x prime, so it comes to x prime. So after a small disturbance, the system goes over to solid phase. This X state is called the supercooled state. So S is basically X state is called a supercooled liquid. Supercooled liquid. So this is a very peculiar state, which is a state below the melting point, but still it exists. Existence has been proven in several situations, but a slight disturbance actually pulls the system down to a solid state. So that state is another important state that can be obtained in this particular curve. Now coming back to the question, then when I actually reduce the pressure, I can manipulate the mu versus T line. So I can push the line even below the melting point. So what should be such a situation? So vary the pressure in such a way that mu versus T curve goes below T melting point. So I can shift this curve away from this and below the melting point. Let us see what in the picture, that is mu versus T, and you have this one and this one. This is basically, this is for the solid, this is for liquid, steeper curve, and we have still a steep curve, but we put it here. This is the gaseous phase. So this is a state that is an interesting state where this is the melting point. This corresponds to a T melting point, and this is a point which is interesting because it crosses the gas curve and the solid curve. So crossing of the gas and solid curves gives a new point of equilibrium, and this is something. It means it is another T, and it for this state, this is the state with lowest chemical potential, but above this T, it becomes gas. So this is called basically a sublimation. So you go from solid to a gaseous state. So at this point, mu of solid when Ts with particular pressure is equal to mu of gas at Ts P. So this is a new equilibrium that can be found out, and it is because of the fact that we can manipulate this mu versus T curve as a function of pressure also. So that leads to a new condition where your sublimation temperature is lies below the melting point, so that the solid goes over to gaseous state directly without intervention of any liquid state. So that is another thing that we must note. And lastly, there is another interesting point here that we may note, that this crossing may be of another type. Mu versus T curve, if it happens that this is for the solid, this is for the liquid, and the pressure is such that it also cross, the gas line also cross this point. So this is a gaseous point. So at this point, you have an equilibrium and the coexistence of all three phases. So it is a point, it is called triple point, at which at T triple gas, solid and liquid phase coexist. They coexist such that we have a condition solid equal to T P equal to mu liquid Tp equal to mu gas Tp, and the Tp is basically unique because you have two sets of equation. This is one set of equation and this is another set of equation, and if there are two unknowns, that T and P are the two unknowns for two equations, then T and P are automatically fixed. So the T and P are basically unique points. So this point is unique point and characteristic of the system itself. So the triple point is basically a unique point. Triple point is an unique point for the system. So with this we stop here and we go over to more quantitative description of the thing in terms of new equation, which is called Clapeyron equation, in my next lecture. So thank you all for your attention.